Hello there, fellow mathematicians. Welcome to the final episode of Recitation Math 141 Summer 2020, episode 21, where we are coming out of our shells. We have learned all kinds of beautiful mathematics this semester. We are all now calculus experts, and we are ready to take that knowledge and break out of our mathematical shells and take over the world with it. Today, in our final video, our final venture together, we are going to be learning about how to calculate volumes using cylindrical shells. So this section is going to be quite similar to the previous, to the washer and disk methods, but with a little bit of a fun little twist. So without further ado, let's get going. This is just like the previous homework assignment on the shorter side, only 8 problems. So I have chosen 3 of them to do here. Probably will not take the full hour, but given that it's 37.5% of the homework, I feel as though that's a good amount, and that will leave plenty for you to do as well. I hope that once you see a couple of these problems, you should be in great shape to tackle the rest. They will, in general, tend to work pretty similarly. So for this first problem, we are going to use the shell method to find the volume of the solid generated by revolving the regions bounded by the curves and lines about the y-axis. So the curves and lines which we are given y equals x squared, y equals 3 minus 2x, x equals 0, and then we are going to want to look at, in particular, the x values greater than or equal to 0. Okay, so this will give us 2 regions that we could potentially work over, but they're emphasizing here, they're making clear which region they want us to look at. So just like we did in the previous video, whenever we were calculating volumes using the disk and washer methods, I think that the easiest thing, or the best thing you can do to get started with these types of problems is to once again draw pictures. So let me draw my picture. Okay, and we're going to go ahead and graph these curves and lines. Well, I'm going to start at the bottom actually, because x equals 0. This is a fancy way of saying the y-axis, right? So that's one of our lines here, is just the y-axis. We got x and y. Okay, we've got y equals 3 minus 2x. Okay, so that's going to be the line. We love slope-intercept form, right? That's going to be the line. Let's see, it goes up here, y equals 3. And then it has a slope of negative 2. So I'm just going to sketch it. It doesn't have to be perfect, but it's going to look something like that. Okay, so this is y equals 3 minus 2x. And finally, we have the curve y equals x squared. This is a good old-fashioned parabola, so it goes like this, okay? And so you can see, especially, perhaps I should, if I continue this parabola upward, you'll see that this does in fact bound 2 different regions, right? We've got a region to the left of the x-axis, if I were to continue this line a little bit further, and we've got this region to the right of the x-axis, and because they clarify that we're rotating the region for x greater than or equal to 0, that tells us, oh, okay, they want this region here to the right of the y-axis. Okay, so that is our region. Let me go ahead and label this curve. This is y equals x squared. Okay, and so this brings us to this notion of the shell height and the shell radius. Okay, so the way that your textbook describes, and I'll be honest with you, I hadn't seen this method explicitly laid out like this before, but it's a cute little method and I like it. So let's go ahead and explain. Well, first of all, let's go ahead and write down the formula which we're going to need. So the formula which we're going to use, we're going to integrate from a to b. We'll explain what the bounds are in a minute. It's going to be 2 pi, and then we're going to have the shell radius times the shell height. And then all of that will be dx or dy, depending upon the setup. In this case, we'll just write dx, but of course, this would work just the same if you were looking at dy. Your functions would just be functions of y instead of x. So what are these shell radius and shell height things? What's up with them? So the way that you find them, again, I think it's fairly cute. So to find the shell height, what you do is you, how do I say this? Basically, you're going to draw a line segment parallel to the axis of revolution and determine its length / height. So let me say what I think whenever I draw the picture, it'll make more sense. And determine its length or height. When I say length or height, so if our axis of revolution was the x-axis, then our line segment, since it's parallel to the axis of revolution, our line segment would be horizontal. So in that case, we'd be talking about length, whereas as in this case, our axis of revolution is the y-axis. So we want to, so we are instead going to consider its height. Okay, so let's go ahead and figure that out first. So if we look at our region, and let me sketch a line segment through our region here. What I want to know is, what is the height of this region? What is the height of this? And of course, I don't mean at this specific x value. I mean a general formula for the height, which will work whether I'm at this x value, this other x value, no matter where I am. Okay? Well, this goes back to the notion of finding the area between two curves. If I want to know the height, say, of this little olive green region here, the height of that line segment, well, that's just going to be the value of this top function. Here we can see that the function on top over this region is y equals 3 minus 2x, minus the bottom region, which in this case is y equals x squared. Okay, and same thing, of course, for this this right-hand green segment, right? The height of that second line segment is still just the value of 3 minus 2x. Subtract a minus the value of x squared. Okay, so in this case, we have height. I'll write shell height just to be clear. So in this case, we have shell height is given by that top function, which was 3 minus 2x. And then minus the bottom function, which was x squared. And we can just write this as 3 minus 2x minus x squared. So that's the shell height. To find the shell radius, this is essentially the opposite thing. So this we're going to, this actually, I think it's more at the ideas from the previous section, in which I want to know, I just lost my train of thought. Oh, sorry. So I want to know then what the, so if I draw this line segment here, if I draw this perpendicular line segment, well, what is its length? What is the length of this perpendicular line segment? And as we can see, this is just going to come out to be x. Okay, this is just x because we go out and we keep going until we get to whatever x is. Okay, so in this case, the shell radius is simply, so this is kind of the same idea, but with perpendiculars. Okay, and so in this case, we have the radius is x. Okay, this one, again, it's a little bit tricky to try to explain in words. It's essentially just how far it's, excuse me, the textbook describes this much better than I do. Let me rewrite this. No, eraser. So the way that the textbook describes it, I like this description, is distance from the axis of revolution. Distance from axis of revolution. So if I go up and I look at this green segment here, let's say the left-hand green segment, basically what I'm asking is how far away from the axis of revolution, which in this case is the y-axis, is this line segment? And the answer comes out to just be whatever the value of x is, right? That's how far away it is. So in this case, shell radius equals x. So now we have almost all the information that we need. Whenever I integrate, my bounds are going to be x values because this is a dx problem, right? Our functions are in terms of x, so this is going to be dx. So our bounds are going to be x values. We can see right away that the left-hand bound, the x value at which we are starting is 0. Right, we're starting here at the y-axis, so we're starting at x equals 0. But then we need to determine the value of the x value of this intersection point. The way that we do that, so to find b, we need to find the x value of the intersection point of the two curves. So what we do is we set the two curves equal to each other and solve for x. Set curves equal and solve for x. So in this case, our two curves are 3 minus 2x and x squared. Okay, so 3 minus 2x equals x squared. Well, this is the same as 0 equals x squared plus 2x minus 3. And that's the same as 0 equals x plus 3, x minus 1. Which means we have x equals minus 3, and positive 1. Now in this case, we can see from the picture that we are interested in the value of x which is greater than 0. So in this case, we want x equals 1. So this point, we know its x-coordinate is 1. In fact, by plugging x equals 1 into this formula, y equals x squared, we can further find that y here is also equal to 1. But what we really needed was just that x-coordinate. So now we are all good to integrate. We want to integrate from 0 to 1. Okay, remember we have 2 pi. And then we're going to multiply these two things together, the shell radius and the shell height. The shell height is 3 minus 2x minus x squared. So 3 minus 2x minus x squared. And then the shell height, or shell radius. Which one is it? Shell radius is x. Okay. And why don't we go ahead and work this out? 2 pi integral from 0 to 1. 3x minus 2x squared minus x cubed dx. And I think that I will leave it to you to finish from here. This is a very nice and straightforward integral, right? Just a little bit of power rule here. Raise the exponent by 1, divide by a new exponent, and then plug in your bounds. So I will leave it to you to finish from there. The important part of these, of course, it's important to finish it at the end. Perhaps I should say the most challenging part, or really the part that's new in this section here, is setting up this integral with the shell radius and shell height. I imagine that for most of these problems, once you have that figured out, the integral will not be too terrible. Okay, so that is the first problem of the day. The second problem is problem 5, which will have a similar vibe, but this time we're going to be looking at the x-axis instead of the y-axis as our axis of revolution. So we are going to use the shell method to find the volume of the solid generated. Also, this time they give us a picture, which is very nice and convenient. Generated by revolving the shaded region about the x-axis. Okay, now let me go ahead and sketch this picture. Okay, so it looks like we go like this. Okay, so I've got x-axis and y-axis, x and y. Remember, the x is the axis of revolution in this case. Okay, so we're going to have our curve now is going to look a little something like this. Let me try my best to sketch it here. It goes like something like this, and then it shoots off. And we also are bounded by this line here. Okay, so here we have the line, this is the line y equals root 3. That's this horizontal line. This curve here is x equals 2y squared. Okay, and so the region which we're going to rotate, or excuse me, revolve, is this blue region here. Okay, so once again, the general formula, let's jot that down one more time. It's going to be the integral from a to b of 2 pi shell height. It doesn't matter if you write shell height first or shell radius, because multiplication is commutative, meaning that you can flip the order, of course. Now, with this time, it is going to be a dy problem, because you'll notice that our function, x equals 2y squared, is given as a function of y. Also, the bound y equals root 3 is given as, of course, a function of y. Okay, so now we once again want to find our shell height and shell radius. Let's start with the shell height like we did previously. So the shell height So let's review what that means real quick. The shell height, what we're going to do is we're going to draw a line segment parallel to the axis of revolution, and we're going to determine its length. So the axis of revolution in this problem is the x-axis. So we're going to sketch our horizontal segment. Our segment is going to be horizontal and look something like this, right? Well, we can see that the length of this thing, well, it's just whatever this x-coordinate is, right? The length of this thing is just whatever the x-coordinate is, and the x-coordinate is given by 2y squared. So like we said, here we're given functions of y instead of functions of x. So the shell height, I'll just write it this way, shell height is going to be given by 2y squared. Okay? Now the shell radius, let's review what that means real quick. So the shell radius, that is the distance from the axis of revolution. So as I look here, if I wanted to see how far I have to go from the axis of revolution to get here, it looks like this is going to be given, this is just whatever the y, this is just y, right? This is just whatever the y coordinate is. So it looks like the shell radius is just going to, in this case, be equal to y. You'll notice that in both of our problems so far, the shell radius has just been x or y. And while, of course, things won't always be quite that simple necessarily, they oftentimes will. You will notice, I think in general, that those things tend to be a bit simpler and more straightforward than perhaps the height. The height is really more interesting usually. Okay, so we've got our shell height, we've got our shell radius. Let's check out our bounds. Well, our bounds, remember, are going to be y values. So let me jot that down because that's important. The bounds here are y values because we're integrating with respect to y. Because we are integrating with respect to y, and in this case, we can see that our y values are very nicely defined for us. We can see that we're starting from y equals 0 down here at the origin, and we're going until we hit the line y equals root 3. So the volume, in this case, will be, we're going to go from 0 to root 3. Once again, we have 2 pi. Okay, our shell height is given by 2y squared. And our shell radius is given by y dy. Once again, from here, this is a fairly straightforward integral. Okay. One fact, I will leave it to you to finish, but I will leave you with the helpful hint or helpful reminder, perhaps, that if I have the square root of 3 and I raise it to the 4th power, well, that's the same thing as the square root of 3 squared. Well, the square root of 3 squared, that's just 3. And so that's 3 squared, which is 9. So take this as a hint as well. Of course, your numbers might look a little bit different, but this general algebraic tip might be helpful for you. And you should, hint, this kind of thing should come in handy toward the end of this problem. All right. That wraps it up for problem 5. Finally, we have problem 7, and that will do it for this video, and sadly for this class, at least as far as I'm concerned. Of course, you are welcome. I have an office hour on Thursday, and of course, if you have questions, please just ask them. But in terms of the formal recitation videos, sadly, this is it. Use the shell method to find the volume generated by revolving the region, generated by revolving the region bounded by x equals 14y minus y squared, and x equals 0 about the x-axis. All right. They do not give us a picture this time, but that's okay. That gives us the creative liberty to sketch our own picture and write our own history. Let's get going. Okay, so my curves, we've got, okay, the region bounded by, okay, well, x equals 0. Let's start here because this is just the y-axis again, right? Just the y-axis. So let's go ahead and sketch 14y minus y squared. Well, I will admit I do not know, I most certainly do not know exactly what that looks like, and I'm not going to sit here and compute a bunch of points. But I know, generally speaking, it is going to look something 14 of x equals I think, hang on a minute. X equals 14y minus y squared. Oh, okay. So I don't know exactly where the vertex is. Right, it looks like I'm going to have x equals 14y minus y squared. Something is throwing me off here. What is it? Something's throwing me off here. Okay, I am going to go ahead and plot a few points actually, because something I can't quite, for whatever reason, I'm looking at this and I'm getting myself confused. But the nice thing about about graphing things is if we get confused, we can just take a minute, step back, and plot a few points. Okay, so I'm actually going to, instead of picking x values, I'm going to pick some y values to look at. -1, or -2, -1, 0, 1, 2. I'm doing that because our function is given in terms of x, or it's a function of y. So let's see, if I plug in y equals -1, then I get x. Oh, I see why I was confused. Okay, I do see why I was confused. Let's go ahead and okay, I know how to sketch this. So this looks vaguely, I don't need you, I'm sorry, table. This looks vaguely like it's going to be a parabola and it's going to open to the left. Okay, it's going to go through the origin here and it's going to look something, probably something more like this. Or no, like this. Yeah. Yeah, so it's going to look something like this. Oh, no, something like this. There we go. All right. And I want the region bounded by x equals 14y. Okay, you know what? I am going to calculate a few points. I am sorry I keep talking myself in circles here. Okay, so if I plug in y equals -2, then I'm going to get, let's see, -28 minus 4. So then x is -32. If I plug in y equals -1, then I'm going to get -14 minus 1 is -15. If I plug in y equals 0, then I get x equals 0. If I plug in y equals 1, then I get 14 minus 1 is 13. If I plug in y equals 2, then I get 28 minus 4. Okay, 28 minus 4 is 24. And so it looks like what we're doing, so as y gets bigger, as we're moving up, I'm moving let's keep going a little bit further out and see what happens. Y equals 3, then I get 14 times 3 is 42 minus 9 is 33. Y equals 4. 56 minus 16 is 40. Okay. So this looks a little something like this. It looks something like this. So it looks like it's actually, and this is not at all to scale, but it looks more like that. Okay, this makes more sense. So now this is our region. I apologize, that took me a minute. As you can see, I struggle to understand graphs as well sometimes. Okay, so our graph looks something like this. This is our region, the yellow region. Once again, we're going to need volume. It's the integral from a to b of 2 pi shell radius, shell height, radius, shell height. And then is it going to be dy or dx? Well, we're revolving. We've got our function as a function of terms in terms of y, so we're going to write that dy. Okay, whew. So what I need, first let's go ahead and find our bounds of integration. Let's start with that this time. So I know down here, this is the point 0, 0. Remember, my bounds are going to be y values. So what I want to do is to find b. Just like before, I'm going to set x equal to, so I'm going to set x equal to 0. So I'm going to set 0 equals 14y minus y squared and solve for y. Okay, well, this is the same as 0 equals 14 minus y, which means y equals 14. And of course, we get the solution y equals 0 here as well, because we divided both sides by y. Okay, so y equals 14, and so that is the value up here. I don't really, so this is the point 0, 14. Okay, so those give us our bounds. Now we need to find the, let's start with the shell height. Okay, so let's start with shell height, which you'll recall, we're going to draw a line segment parallel to the axis of revolution. Okay, so parallel to the axis of revolution. In this case, the axis of revolution is the x-axis. So it's going to look something like this. Okay. The length of that is given by the x-coordinate, which in this case is 14y minus y squared, because x equals 14y minus y squared. So 14y minus y squared. And then if I look at the distance from the axis of revolution to that little line segment, that gives me my shell height, or shell radius, shell radius. So that's just y in this case, right? It's just whatever that y coordinate is. So I will leave you to integrate, but the integral is going to look like the integral from 0 to 14, 2 pi times 14y minus y squared times y, dy. And I will leave it to you to finish it up from there. So that does it for this video, and sadly for all of our videos for Math 141 Summer 2020 Recitation. I hope that you guys have enjoyed it. I hope most importantly that you found these videos to be helpful. Please let me know if I can do anything to help you get ready for the final exam. You guys worked really hard. Your last exam grades were awesome, so great work with that. And let's finish this semester strong with one more strong exam here at the end. So thank you guys for a great summer. I hope that you enjoy the rest of your summer, whether you're taking courses in summer session 2 or not. For those of you going on to Calc 2, I absolutely love Calc 2. And you should feel free to always reach out to me in the future if you have questions. I will be more than happy to help you in the future as well if you need it. So please don't be shy to reach out. Thanks again, guys. Good luck with the final, and